everyone, this is Yawen Wang from Stanford University. Today I'll present our work on SmartHarvest, harvesting idle CPUs safely and efficiently in the cloud. This is joint work done in collaboration between Stanford University and Microsoft Research. Cloud computing has emerged as the dominant platform for computing in recent years. However, despite its growing popularity, the underlying resources in the cloud are not always getting effectively utilized. This figure shows 2017 data from Microsoft, which reported that 60% of the VMs running on Azure has an average CPU utilization of below 20%. The common reason for CPU underutilization in the cloud is that users often over-provision their VMs based on the peak load, and this is especially true for user-facing workloads that require consistent low latency. One common way to improve CPU utilization is to use spare resources from latency-sensitive workloads to run batch processing tasks. In order to do this safely without violating performance constraints of latency-sensitive workloads, prior works have either required extensive offline workload profiling or knowing application-level characteristics. Unfortunately, these prior approaches are not applicable in public cloud. And this is because VMs are often opaque boxes in public cloud. Cloud providers have no knowledge of what is running inside the VM. Therefore, in public cloud, we can only monitor VMs with low-level counters such as their CPU usage. And to be more careful when borrowing cores from VMs, we should be conservative and assume that any VM may be running latency-sensitive workload. We are proposing a new solution called SmartHarvest to improve CPU utilization in the cloud. It uses online learning to continuously learn and predict future CPU usage of opaque customer primary VMs based on their past usage. It safely harvests unused cores from primary VMs to run low-priority batch processing jobs inside a new type of VM called Elastic VM. It uses a two-level safeguard design to help reduce performance impact on primary VMs when the learning model frequently underpredicts their CPU demands. At runtime, SmartHarvest dynamically allocates cores among VMs to minimize impact on primary VMs while maximizing the number of cores harvested. I'll next describe Elastic VM, a new type of VM that we're introducing. Elastic VM runs batch workloads on idle cores unused by primary VMs. It has a minimum set of guaranteed resources. It will not be launched if there's not enough resources on the server to meet this minimum. It has lower priority than primary customer VMs, and the number of cores assigned to it will change dynamically based on CPU usage from primary VMs. Lastly, it's configured to have as many virtual cores as the total number of physical cores on the server, so it can always make effective use of any harvested cores. Let's now go over the high-level design of SmartHarvest to see how it works. In this diagram, the orange box shows a 10-core primary VM that is currently using 5 out of its 10 allocated cores. The green box shows the Elastic VM, which starts with a single core. The gray box shows the main root partition of Hyper-V on the server, where we run the EVM agent. The EVM agent is responsible for monitoring server-wide CPU usage, learning and predicting CPU usage of primary VMs, and reassigning cores among primary VMs and the Elastic VM. Let's suppose that the EVM agent predicts the primary VM will need a peak of 7 cores for time window Ti. Then the agent can shrink the CPU size of the primary VM to 7 and reassign the remaining 3 idle cores to the Elastic VM. This leaves primary VM with an idle buffer of 2 cores. The idle buffer can help absorb any bursts from primary VM during time window Ti. If at the end of Ti, we observe that the peak usage of primary VM was 6 cores, then we have provisioned enough cores to observe the true CPU peak usage of the primary VM. And we now have full feedback for the agent to update the learning model and make a new prediction for the next time window. Based on the predicted peak, the agent can then adjust the VM sizes accordingly. Let's now consider a different situation. Let's suppose the primary VM uses up all its assigned cores during Ti. Then we have a safety violation because the primary VM could have needed more cores, hence suffering from performance loss. In this case, we don't know what the true peak usage of the primary VM is. So we only have a partial feedback. Without knowledge of the true peak, We will not update the model. The agent now conservatively estimates primary VM CPU peak for the next time window to be 1 plus peak observed over the last second, and return cores from elastic VM to the primary VM. We call this actions as a short-term safeguard in SmartHarvest, and it is triggered when we don't have full feedback information to utilize the learning model. Additionally, the EVM agent monitors the primary VM's vCPU wait time to be dispatched onto physical cores, and we use that as a proxy for VM performance. When the primary VM experiences long vCPU wait time, the agent returns all its cores back. We call this a long-term safeguard. It is triggered when we can infer performance degradation of primary VM from long vCPU wait time. This could happen if the workload run inside primary VM is unlearnable, and the agent continuously underpredicts its CPU usage. Next, I will discuss how SmartHarvest predicts VM CPU usage to help safely harvest unused cores. The constantly changing CPU utilization of VMs makes it challenging to accurately predict future usage. To address this challenge, we use an online learning algorithm in SmartHarvest, which updates the model with each newly observed data point. The online learning approach obviates offline training and profiling, making it possible to learn different workload characteristics after they've started. We also choose to make predictions of CPU usage of primary VMs on a fine-time granularity of every 25 milliseconds. This helps the learning model quickly detect changes in CPU usage patterns and adapt to them. The prediction target is the peak CPU usage in number of cores of the primary VM for the next 25 milliseconds. The set of features we use include 5 simple statistics: average standard deviation, minimum, maximum, and median, computed from past CPU usage data of the primary VM. We considered additional features such as different percentiles, but found these 5 features to be the most useful. When deciding what model to use for online learning, we considered 2 requirements. First, we want the model to be simple and lightweight, so it takes less computation resources and can make frequent predictions. This leaves complicated models such as neural network out of consideration. Secondly, we want to be able to differentiate between under and over predictions when updating the model. Under predicting CPU peak of primary VMs is a more severe problem because it could negatively impact primary performance. With these 2 requirements in mind, we decided to use a cost-sensitive multi-class classification model in SmartHarvest. It trains a separate linear regression model for each class, where the class label represents the peak number of cores needed by the primary VM for the next time window. The class with the lowest predicted cost is chosen as a prediction. It allows flexible cost assignment to different class labels. It also provides fast prediction and update times, which take less than 15 microseconds on average in our implementation. When we know the true peak CPU usage of a primary VM from a time window, we have full feedback to assign a cost to each class label and update the model. This figure shows the example cost function we use to assign cost to class labels for a 6-core primary VM. The cost linearly increases as the class label becomes further away from the true peak. Based on the true peak usage, classes that were under-predicting are penalized more to skew the model away from aggressive harvesting. On the right, it shows the cost assignments for a 6-core primary VM, where the true CPU peak for a given time window is observed to be 3 cores. We can see that classes that would underpredict have significantly higher costs than classes that would overpredict. For evaluation, we run 4 different latency-sensitive workloads in the primary VM. We look at their P99 latency to measure the impact of harvesting on their performance. For the elastic VM, we run CPU Bully, a synthetic CPU-bound workload that helps estimate the number of harvest cores. We compare SmartHarvest with 2 alternative harvesting policies. The fixed buffer policy dynamically adjusts primary VM CPU size to ensure there's always a fixed number of cores in the idle buffer. The previous peak policy simply estimates peak usage of the primary VM based on the recent peak observed over the last 25 milliseconds. We conducted our experiments on an Intel server running the Hyper-V hypervisor. Let's now look at some results when we co-locate a single 10-core primary VM with an elastic VM. For each experiment, we run a different latency-sensitive workload in the primary VM and the CPU Bully inside the elastic VM. Each experiment lasts for a minute. The set of figures here shows the baseline P99 latency for each primary workload when no core is harvested. The horizontal line marks a 10% increase from the baseline P99 latency. Let's first look at the performance of different fixed buffer policy. Each data point is denoted with the corresponding fixed buffer size next to it. The general trend for the fixed buffer policy can be observed across workloads. As we increase the size of the fixed buffer, the impact on the P99 latency decreases, but it also harvests fewer cores. When we pick out a single best fixed buffer size that harvests the most while staying below the 10% increase, it is different for each workload. This is expected as each workload exhibits a different CPU usage pattern. For the previous peak policy, we noticed that it can significantly increase the P99 latency for some workloads. This is due to sudden increases in CPU usage that is not captured from the recent peak usage. Finally, let's look at the results for SmartHarvest. With the predictive power of online learning, it consistently harvests 1.5 to 3.5 cores across different workloads without per application tuning or any knowledge of application level information. At the same time, SmartHarvest also has less than 10% impact on P99 latency for our workloads. When we look at all the results side by side, we can see that SmartHarvest outperforms alternative policies by harvesting a good amount of idle CPU resources while maintaining a small impact on different latency sensitive workloads. We have completed a more thorough evaluation of SmartHarvest. Due to the limited time, these additional results are not covered in this talk, but we invite you to read about them in our paper. In conclusion, we have designed SmartHarvest to manage CPU resources in the cloud with online learning. It automatically learns and adapts to CPU usage of different applications and varying load patterns inside opaque primary VMs. It harvests spare CPU cores while minimizing performance impacts on primary VMs. And the evaluation results show that it can effectively improve CPU utilization in the cloud. Thank you, and you can contact me via email for any questions.